Hi everybody, welcome back to another video on Feynman integration. Today we're going to be looking at an integral similar to one we've done before. It was in my first example. We're going to be evaluating this integral from 0 to 1 of x squared minus 1 over natural log x, all of that squared dx. And I believe in my first example, we simply evaluated the same integral, only we weren't squaring it. So we're going to be using two tools today, the Leibniz rule, of course, and then we're going to be using this fact that we discovered in my first example on Feynman integration. Go ahead and watch that again if you want to see how I got to this. But that is true. The integral from 0 to 1, x to the t minus 1 over ln x dx is equal to the natural log of t plus 1. Okay, so to get started on this integral, of course, we're going to reparameterize it. And for those of you that have watched my previous videos, I'm sure you see this step coming. We're going to create a function of t that's equal to the integral from 0 to 1 of x to the t minus 1 over natural log x all squared dx. And you can see I just replaced that 2 with a t. We're going to make our notes here on that function. You notice that if you plug in 0 for t, you'll get 0 for the entire integral. And if you plug in 2 for t, you'll get I, which is what we want. So, using the Leibniz rule, we differentiate f of t by simply taking a partial derivative with respect to t of the inner function. And what you get when you do that is that f prime of t is equal to 2 times the integral of 0 to 1 of x to the t minus 1 over ln x, all that times x to the t dx. And then, to make it a little bit nicer, what we want to do is distribute that x to the t and also break up the integral using linearity. And what you end up with is this right here. And that's all equal to this. And you're probably wondering, well, wait, how did you get that? Those don't look like integrals you can solve normally. They're not. That's where this comes in. We already proved this in a previous video, so it's not a huge step to get from there to there using this, and I'll show you how to do that right now. You'll notice that these integrals are almost in the same form as this one, not quite. They're missing the minus 1. So let's just put a minus 1 here. Well, you can't just change the equation like that, because now it's not the same as it was before. So we need to figure out what we've done to that and then undo it somewhere else. Well, what we've done is we have subtracted 2 times. You see, we subtracted 2 times the integral from 0 to 1 of 1 over natural log x dx. So since we subtracted that, we need to add it back. And we can add it back like that. And you can see that that will actually add it, because this is a negative and they distribute. So we're adding we're adding 2 times the integral from 0 to 1 of the natural log of 1 over, let me say that again. We're adding 2 times the integral from 0 to 1 of 1 over the natural log of x dx. And those are still a little bit messy, but since we already have this tool, all you need to do is, so this is equal to that, because for our t, instead we have 2t. So instead of natural log t plus 1, we have natural log 2t plus 1. And this one is already in the correct form. Okay, so now we have f prime of t, but we don't want f prime of t, we want f of t. So of course we integrate. That's this step down here. Integral of f prime of t is equal to the integral of that junk, which is equal to f of t. And we're going to jump right to f of t, because although this looks a little bit messy right here, you can solve that using, you know, the normal techniques that you'd learn in first and second semester calculus. You just have to know how to take the indefinite integral of the natural log of t. And what you get when you do that is that. It's messy, but you'll find that if you use this fact right here, that f of 0 is equal to 0, you'll find that c is equal to 0. And then plugging in 2 to get I, you find that our original integral is equal to the natural log of 3,125 over 729. And I don't believe that reduces. This number right here is 5 to the 5th, I believe. And this, I believe, is 3 to the 6th. So I don't believe there are any common denominators between them. So that's the final answer. I hope you enjoyed that.